Hey guys, welcome back. Alright, so continuing on with our satellite motion part of gravitational fields. Here's our dot point that we're looking at. Again, it's very concise. It's very actually unclear as to the extent to which you need to talk about this dot point. But we'll try and cover as many things as possible, so if it pops up, then you can use that. Right, so basically we're going to look at where this comes from now. Okay, this equation here. In the last video, we just talked about what satellite motion was, what Kepler's laws of satellite motion are, that every planet orbits the sun in what we call an ellipse. And in fact, every object that orbits something else will orbit in an elliptical path. Doesn't have to be a planet orbiting the sun. Could be the moon orbiting the Earth. Could be a satellite orbiting the Earth. Could be a satellite orbiting the moon. Who knows, okay? Anything that's orbiting something else travels in an elliptical path with the central sort of mass located at a focus of that ellipse. The second law said that a satellite sweeps out equal areas in equal time intervals. So you can go back at the previous video and look at a nice little diagram that explains that there. And the third one is most relevant. It stated that the cube of the average orbital radius divided by the square of the orbital period is some number, some value. And that value is the same for all objects that are orbiting the central body, the central mass. Okay. In particular, Kepler framed it as talking about planets orbiting the sun. So let's just generalize it a bit more and talk about general satellite motion and see where this equation pops out. So what do we want to know about satellites orbiting things? Okay, well, you'd like to know their orbital radius. You'd probably like to know their orbital velocity. What else? You'd probably like to know their orbital period. Okay, so really we're trying to look for orbital speed, orbital radius, and orbital period. Okay, those three things are really important for trying to analyze the motion of some kind of satellite or planet. Let's start by talking about the velocity. The orbital radius, that's pretty... we've got ways of measuring how far away things are based on, light. We're not going to get into that here. So, we don't really have to talk about a way to calculate R based on some sort of fundamental thing. Velocity, though, we can because that's a little bit tricky. But we still can measure it in certain ways. So, anyway, let's not go there. So let's talk about orbital speed. So what is speed? Well, average speed, if you're assuming a nice, stable, circular, constant, uniform orbit, which is what we're talking about, okay? Go back to the dot point. We are modeling satellite motion as uniform circular orbital motion. So things are traveling at a steady speed in a circle. So the average speed would be the same as the instantaneous speed in that case. All right, and then this thing here is the average speed of something that's moving. Okay, average speed is equal to distance traveled in a certain period of time. Okay, that's your average speed, which for uniform circular motion is instantaneous speed. If we're talking about circular orbits, then let's say that you orbit something once. So you start here and you go around and you end up back where you started. Well, how far have you gone? Well, you've just traveled the circumference of this particular circle, which is 2 pi r. The time that it took for you to do that, well, you've just completed one orbit. So we call that an orbital period. So the time taken is just the orbital period. Now, if you just use this definition of speed, replacing delta x and delta t with what we just stated, you end up with this. Okay, so that's your average orbital velocity. If you're talking about circular motion, it's just your orbital velocity. Okay, but really we know that orbits are ellipses, so we sort of have to say it's the average. Okay. All right, so that gives us a way to calculate the average orbital velocity. If we know how far away that satellite is, that's r, and we know its orbital period t. Those two things are pretty easy to find. Okay. All right, so now we can start talking about its acceleration because we've now worked out its velocity. And you've got to go and think back to circular motion when we did area of study 3. We're talking about centripetal acceleration. Okay, it's the acceleration that's causing it to continuously change its trajectory, I guess you could say. Now for things in a circular motion, in this case circular orbits, that acceleration is given by this equation here. Okay, acceleration is v squared over r. V is the orbital speed, r is the orbital radius. If we now take what we just found the speed to be, so v is equal to 2 pi r over t, and I substitute that into this expression for a, well, that's what I do in this line here. Okay, so v squared, well, that's like saying 2 pi r over t squared. 2 squared is 4, pi squared is pi squared, r squared is r squared, t squared is t squared on the bottom there, but it's multiplied with that r because there's already an r in the bottom of your fraction. Okay, notice that you can cancel that r on the bottom with one of the r's on the top, leaving you with a equals 4 pi squared r over t squared. Okay, there you go. So that's kind of almost looking like this thing that we've got up here. In fact, it is looking like this thing that we've got up here. Okay, that's the 4 pi squared r over t squared. There you go. That's a way to work out the centripetal acceleration of a satellite if you know its radius and its period. Cool. What else can we do with that? Well, remember a few videos ago, back in the notes, we mentioned that acceleration due to gravity, which is this centripetal acceleration that's keeping this object in a circular orbit, that is equivalent to gravitational field strength at that particular distance. Okay, now if we were in uniform circular motion, then the distance that the satellite is from the main object, well, that's not changing. Okay, the distance is constant because it's traveling in a circle, right? So its gravitational field strength at that distance, well, that we can work out using gm over r squared. Just don't get confused. This m here is the mass of the central body. Okay, it's the mass of the thing that the satellite is orbiting. It's not the mass of the satellite itself. All right, and what we can say is that gravitational field strength g, well, that's just equal to centripetal acceleration a, and I can just make this thing equal to this thing, and that's exactly what we have there. Okay, cool. Now we can put all of these things together. So we've got v, a, mass of the central body, orbital radius, orbital period. Let's stick them all together in one line in like a multi-equation equation. So let's see what that looks like. Next slide, please. What's going on? Lag. There we go. Cool. So this you should put onto your cheat sheet. Okay. I don't think that this particular sort of setup is not, I don't think that's on your data booklet that you're going to get in the exam. I'll have to double check. Don't have it in front of me. But I think they will probably have this one. They would probably have this one. Don't know about this one. Okay, so make sure you've written that down somewhere. And all you've got to do when you're faced with a question about like satellite motion and things orbiting other things, just write down what you've been given. Okay, you'll always know big G. Big G is just the constant. Okay, write down what you've been given. Have you been given V, A, little g, the mass of the central body, or the orbital radius? Have you been given any of those things? Yeah, all right, write them down. Then write down the thing that you're trying to find, and then just pick, you know, two of these things out of this like sort of like multi-equation thing that we've got going on. Pick two of them that have all the quantities that you've been given as well as the one that you're trying to find. Okay, just like you would with a projectile motion question where you've got to select your kinematic equation. All right, so that's your strategy. We'll do some questions in the next video. That's it for now. Okay, so just make sure you've got that written down somewhere. That's your equation that we're going to be using. All right, so we'll stop there and I'll see you in the next video.